Bismillahirrahmanirrahim. In this lecture, I will discuss losses in DC machines and the efficiency of a DC machine. So, there are three types of losses in a DC generator or a DC motor. First loss is called iron loss. This loss is also called core loss. This is also called magnetic loss. Iron losses, core losses, and magnetic losses, they are same, and the iron losses are produced in the DC generator due to the rotation of iron core of the armature in magnetic flux. There are some losses taking place in the core and are known as iron losses or core losses. So, core losses or iron losses are of two types: hysteresis losses and eddy current losses. Hysteresis loss is the loss which occurs due to the reversal of magnetization of the armature core. This loss depends on the volume and grade of iron, maximum value of flux density Vmax, and frequency of magnetic reversals. The mathematical expression of the hysteresis loss is eta Bmax raised to power 1.6 F into V, and this expression is also called Steinmetz formula. Here V is the volume of the core, eta is the Steinmetz hysteresis coefficient, and this is a material specific quantity. F is the frequency of magnetic reversals, and mathematically F is equal to Pn divided by 120. If you remember, while discussing the AC machines lectures, uh, we studied that the synchronous speed of the induction motor or the synchronous motor is equal to 120 F over P, right? So in that case, N was the synchronous speed, or this was the speed of the revolving magnetic field in RPM. So frequency is will be equal to Pn divided by 120 by rearranging this equation. Here P is the number of poles in the DC generator and N is the RPM of the DC generator, and this is 120. So this is the frequency of the magnetic reversals, and it directly depends on the speed of rotation of the armature core in the magnetic flux. In DC, in AC machines, that F was equal to the frequency of the AC supply, but since we are discussing DC machines, so the frequency of the input supply will be equal to zero. But for calculating the hysteresis loss, the frequency used is that of the magnetic reversal, and it will be calculated by this expression. Second, iron loss is the eddy current loss, and when armature core rotates, it also cuts the magnetic flux. Hence, EMF is induced in the body of the core. This EMF sets up current in the body of the core due to its small resistance. So, the core is having a very small resistance due to the rotation of the armature core, which is made up of iron. The flux is continuously changing, so EMF is induced in the core, and due to that EMF, small currents also produce within the body of the core, right? So that current is called as eddy current. The mathematical expression of eddy current is WE equal to K Bmax square F square T square V square. Here K is the eddy current coefficient or eddy current constant. Bmax is the maximum magnetic flux density. F is the frequency of magnetic reversals. T is the thickness of the lamination, and V is the volume of the armature core. So in order to minimize the eddy current, we have to use laminated iron core, laminated sheets, and they are joined together, and in between we place some laminations. So the thickness of that lamination is actually T, which we see in this expression. So smaller the thickness, smaller will be the eddy current loss. So eddy current flows perpendicular to the flow of magnetic flux. So this current intercepts B. So that will cause distortion of the magnetic flux. And due to this distortion in the magnetic flux, less EMF will be induced across the DC generator. So we will get small electrical power at the output of the DC generator due to this eddy current loss. The eddy current loss should be minimum so that we get maximum induced EMF at the output terminals of the DC generator. So total losses in a DC generator are copper losses, iron losses, or core losses or magnetic losses, and the mechanical losses. So copper losses are of three types: armature copper loss. Mathematically, they are written as Ia square Ra. Similarly, field copper loss, If square Rf, and brush contact loss. So the copper losses are actually the losses which occur across the copper windings of the DC generator. So armature winding is made of copper material. Similarly, field winding is also made up of copper material. So the losses in the armature and field windings are called armature and field copper losses respectively. Similarly, this is a very small loss which is occurring across the brush contacts. Magnetic losses, which we have already discussed, and the third losses are the mechanical losses, and they occur due to the friction losses at the bearings and the commutator, air friction or windage loss, right? So they are called mechanical losses, and they are 10 to 20% of the full load losses. Magnetic losses and mechanical losses are collectively called as stray losses. So these mechanical losses and the iron losses, they are actually constant losses, but the copper losses are actually variable losses. And in copper losses, only this armature copper loss is actually a variable quantity because this copper loss depends on the armature current and armature current depends on the load current. So if we increase the load, this armature current will increase. Similarly, if we reduce the load, this armature current will decrease. So it means these losses are directly depending on the load. So they are called variable losses. All other losses are called constant losses. So now we will discuss power stages. And first of all, we will discuss mechanical efficiency. Mechanical efficiency is equal to B over A, and B is equal to total watts in armature divided by mechanical power supplied. So total electrical power generated by the armature divided by the mechanical power supplied to the armature. The ratio of these two powers is called mechanical efficiency, and mathematically it is equal to EGIA. EG is the generated EMF in the armature, and here we have output of the driving engine. Similarly, electrical efficiency is the ratio of watts available at the load terminal and total watts generated in the armature. So the ratio of these two powers will give us the electrical efficiency, and mathematically it is equal to C over B, and it is equal to VI over EGIA. So overall or commercial efficiency will be equal to the product of these two efficiencies. So that will be equal to P by A divided by C by B. So that will be equal to C by A. So watts available at load terminal divided by mechanical power supplied. So this is the overall efficiency. And eta C is equal to eta M multiplied by eta I. Now we will discuss condition for maximum efficiency. So the output power of a DC generator is equal to V times I. V is the voltage at the load terminal and I is the load current. Similarly, input power is equal to output power plus losses. So output power is equal to VI, and losses are equal to constant losses plus variable losses. So WC are the constant losses and IA square RA are the variable losses. So VI plus IA is equal to I plus I shunt. So I plus I shunt square RA plus WC. And in this case, efficiency will be equal to P out over P in. So this is P out and this is P in. And we can divide the numerator and the denominator by VI to get this expression. And we have to find out condition for maximum efficiency. So we have to evaluate the maxima of this expression with respect to the armature current. So the maxima of this expression can be evaluated by taking the derivative of this term and equating that derivative to zero. So the derivative of this term can be evaluated uh, by using the dividing rule of the derivative or division property of the derivative, and then equating that derivative formula to zero. So after simplification, we will see that only this term, the derivative of I R A plus V plus W C over V I must be equal to zero. And the derivative of this term is equal to R A divided by V minus WC divided by VI square. So that will be equal to 0. So we are evaluating the condition for maximum efficiency. So we are evaluating the maxima of this efficiency expression. And you might have observed that we have equated IA equal to I, right? So we have assumed that IA armature current is equal to the load current, okay? Because normally this shunt current is very small compared to the armature current, so we can ignore this shunt current, so armature current will be equal to the load current. So that's why we have obtained this expression, and after equating this derivative to 0, we will get this expression, and according to this expression, we can get WC equal to I square RA. So WC equal to I square RA is the condition for maximum efficiency. So this condition is saying that the efficiency will be maximum when constant losses are equal to the variable losses. So these are constant losses. These are the variable losses, which are armature copper loss. So IA can be written as WC divided by RA square root, right? So I will be equal to square root of WC divided by RA. So if our load current or if our armature current is equal to this term constant losses divided by RA square root, then our DC generator will be running at maximum efficiency. So this is the plot of efficiency with respect to the current, and this is the plot of actually this expression. So if you want, you can plot this efficiency using MATLAB. So this expression can be evaluated very easily in MATLAB, and we will see that we are getting such a profile of the efficiency with respect to the current. So when our current is equal to WC over RA square root, that point our efficiency will be maximum, and that current, that mathematical expression of this current is actually lying at some point over here. So this is equal to this current I max, right? So this expression is equal to the current over here, and at this point our efficiency will be maximum. So that is the condition for maximum efficiency which we have mathematically derived, and that was all about our discussion on losses and efficiency of a DC generator. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.